So turn taking is essentially about detecting when the speaker, the human, stopped speaking and detecting that very precisely. Based on that, triggering the bot's reaction. So, for example, the speaker is speaking here, and the bot listens carefully. And this is a moment of pause where the speaker pauses to think, using words like maybe or but. Let me think. And this is a crucial moment of turn taking. The bot, the voice agent, has to decide whether to wait for the user, for the human to resume speaking, or to interrupt and provides its response in context. So as it may happen that the human resumes speaking after this, and the bot can go back to the listening mode and uh, get the full context of the conversation, as opposed to interjecting and destroying the naturalness or fullness of the conversation. The usual way in which this takes place is through a voice activity detector. So as soon as the user stops speaking, within millisecond, the voice detector will say that uh, the speaker has stopped and the bot can take over. And typically, voice detector is controlled by a threshold for how long does it wait after a lack of speech. The issue is especially is particularly instances like this where the user is just thinking, and they're in middle of thought, they're going to resume, but the bot doesn't know that, and it might interject or interrupt very quickly and destroy the conversation. So voice activity detection is the naive implementation, or is the naive way in which you would implement turn detection. The sophisticated way of thinking about it is that to understand what the user has been speaking, the words that the text that the words that the user has been using, and the audio, the intonation, the prosody of the user, and taking that into account where to predict whether the speaker has actually finished what they wanted to say. So why is this hard? Why is turn detection so hard? It's a crucial operation as we discussed, but what makes it really hard is that we want it to be really low latency. Turn changes happen very frequently, or may happen very frequently in a conversation, and you don't want so in a voice agent, typically there's a speech to text detection, there's a TTS model, there is a LLM working to convert what the user said into useful actions, and you don't want the turn detection to take up a lot of time um, to destroy the naturalness of the conversation. So you want low latency and you want it to be fluid. And what do you mean by fluid? We just examine the spectrum of turn detection, the efficiency of turn detection. So if it is too early, if like in the VAD, the VAD voice activity detector case, if it is too early, then the agent would interrupt the speaker before they are finished, and that would be destroying the conversation. On the other side, if the activity detector is too late, you give a lot of time to ensure that speaker has definitely finished speaking. So that will make a sluggish agent. The human would have to wait a long time before the agent responds, and that will make the human impatient. So what we need is sweet spot of a fluid interaction just in time, maybe slightly delayed to ensure that the user has indeed finished what they want to say, and immediately coming in with the bot's response. So this trade-off spectrum of finding the sweet spot where a bot is may come back, may interject, is what makes this problem complicated. And a very interesting ML trade-off. So let's look at the problem in terms of an algorithmic approach. How do you implement turn detection? So you're getting these audio chunks. They're coming in. Is human speech is chunked into audio chunks which are coming in. And what you want to know is when the user has indeed stopped speaking. when they're finished. So essentially, this is a sequence labeling problem. Every chunk gets assigned a probability that the user has is speaking. Speech is on. Okay, so when it's continues on, probability is zero point 0.8. When it's going down, its probability is lowering, and finally zero point 0.4, 0.2, and it's completely speech is finished. And there's complete silence here. So the turn boundary is when you decide to detect the threshold of the probability, where you decide to detect, call it, detect whether the probability of speech is low enough that you can call it that the speaker has stopped speaking. And at that point, you can uh, call the end of turn, and the bot can take over. So what's crucial is this threshold, where you determine based on your detector what is the threshold where the speech has stopped, where you can interpret the probability uh, as if the speech is stopped. And this is the classic machine learning problem trade-off. Uh, you There isn't a fixed value where uh, you definitely know for sure that you're done. You have to play around with the probabilities and thresholds to ensure that to find a working uh, practical value uh, where you can safely assume that the speech has stopped. Let's now discuss how of turn detection. So we discussed earlier VAD, duration based turn detection. So you set up uh, a time duration for which you'll wait after the speech ends, and if no speech comes up in that time, then you say that we have the turn has ended. Okay, so this has we discussed this has the usual problem that the user may pause for some time and then start speaking again, and if the duration isn't enough, then you might get a false positive. Okay, so that's the default and the very fast VAD implementation algorithm which you generally start with, but then you have to move on to more sophisticated machine learning based approaches for turn detection. So there are broadly two types: text and audio based turn detection. Um, let's look at audio based first. Okay, so speech carries a lot of features, characteristics which can help you uh, not just the words, but also the intonation and the prosody. There are a lot of features which you can use to, which the a machine learning model can use to detect if the user actually intended to finish, or they are still thinking and they'll continue. So this sort of semantic turn detection you can do by building a audio based classifier sequence labeler, which takes in a sequence of chunks and uses a bunch of audio features like pitch or energy, pauses, speaking rate, intonation, and so on. So looking at all these features, you can build a audio-based sequence labeler, which detects when the speech is done and outputs a probability of whether the speech is done and this turn has ended, this audio chunk. So both Krisp and Pipecat use different forms of audio labelers. I'll show a comparison table. Krisp can work on a CPU. Pipecat needs GPU to work on, and there are some other features which I'll cover. Okay, the text base, you convert audio to text. Okay, and then you look at the text. So for example, maybe or but. If the last token was maybe or but, then it means that the user is most probably speaking. And then um, again, there are discourse markers like full stop or other markers which can tell the model if to wait or predict the speech is end. And even more complex are hybrid turn detector models, which use both audio and text in a synchronized way to predict that um, the turn has ended or not. So here a quick overview of different models. The VAD based turn detector. It's a very slight model, 260K parameters only, uh, and it runs on a CPU, but its accuracy is low. So that's the default when you start with. And then the smart turn V1 and V2 are from the Pipecat library, and Krisp TT is from Krisp company. The Krisp model is lightweight, runs on CPU. Smart turn models are need a GPU to learn. The smart turn V2 is also relatively lightweight. Okay, and the good part is that the overall accuracy is good for all of these audio-based detectors. So research and practice has concluded that audio-based detectors are pretty good, although Krisp says that they're working on a combined audio and text detector, which might be even more performant. Finally, let's talk about the metrics that are involved in detecting turn detection. How do you quantify whether it's turn detector is good or bad? The mean shift time is the primary metric, which shift time is the duration between the silence ends and the detector detects that a speech has ended. So depending on how quick it is or how sluggish it is, you get a shift time and average it over different test data items and you get the mean shift time. So this essentially characterizes the latency of the turn detector, how lazy it is in detecting, and also the user experience they'll get us. You generally want a very small, short mean shift time. And the other metric is about accuracy, which is false positive. If you've said that the detector says that a turn has ended, but actually it has not. So that's a false positive. And what is the false positive rate? So this is a classic sequence labeling problem. So uh, both accuracy latency trade-offs are bound to happen. And let's look at a diagram which nicely shows the trade-off. So here we have on the y-axis shift probability and the audio finishes after the dark region, black region, audio waveform. And the fast shift, if you have a low threshold on the probability output, then you get a fast shift. And if you have a high threshold, you wait for the probability of output to come to a high level and then you get a slow shift. So slow shift is more cautious, so you get better accuracy, but you lose latency and can feel less responsive. Another graph showing how the trade-off between the false positive rate and the mean shift time. As you allow longer shift time, the FPR rate decreases significantly. So the only problem is if you want to be very quick in detecting, and then the false positive is can be there can be many more false positives. So that's the essence of building a turn detector. You have the model, the sequence labeling model can use either audio or text, and the getting an efficient turn detector means navigating these trade-offs between the mean shift time and the false positives. Finally, let's just conclude with the architectural diagram where it fits in the overall voice agent pipeline. So you start with an audio input where the first part is voice isolation or background voice remover, background noise remover, and then turn detection model comes in very early and therefore it has to be very fast. It takes in these 100 millisecond audio frames, calculates the probability of end of turn for this frame, and if the end of turn is not there, you just continue accumulating those frames, and once end of turn is predicted, then the accumulated frames are sent to the voice AI, or for example, you can just send it to speech to text system, which can analyze and transcribe the accumulated frames. Right, so this is very early part, right, very close to audio input. It can even be implemented in hardware, and it's crucial for the voice agent to appear responsive. The turn detector is extremely crucial. So we'll see, I think, lots of improvements in these models. We just recently semantic turn detection has there's recent interest in it, and I believe there'll be many more improvements there.